let's introduce symmetries. So symmetry is a problem that occurs in many models. Okay, and so symmetry is a mapping from solutions to solution or from non-solutions to solution. And so basically it tells you that you can generate new solutions from a given solution easily. The problem with symmetries is that you will explore them also during the search space exploration. And so you might explore for nothing. Well, it's kind of useless to explore a symmetrical search space. And this is why we want to avoid them. We want to avoid them because we want to explore a smaller search tree. And so it's quite important first to realize that your model contains symmetries and then to think about techniques on how we should remove them. And there are several types of symmetries. I will mention the variable symmetries and the value symmetries here. Let's start with the variable symmetry. A variable symmetry is a bijection that we call sigma here on the variables. And this bijection will preserve the fact that you will have solution and non-solutions. So assume that you have a solution x1 equal to a1, x2 a2, and so on. This is one solution. This is the bijection that you want to apply. If you bijection on the variables like this, okay, and you keep the same values, exactly the same values, preserve the fact that you have a solution here or non-solution, then you have detected a variable symmetry, okay? And the bijection that you found is a variable symmetry. Let's consider one example of a variable symmetry. I want to model the n-queen problem here. Okay, so I have decided to say that this was the queen 1. So there is one variable per queen. The value is the position. I have the queen 1, then I have the queen 2, queen 3, queen 4, and so on. And so I decide at which place I will place the queen. Okay, which cell will contain the queen 1, queen 2, queen 4, and so on. Okay. Then if I apply a bijection, that will simply be an arbitrary bijection between these variables and the n other variables here. I will preserve the solution that I had, right? So if I decide to rename Q1 by Q3, for instance, and that's the only change that I will do, then I will preserve the fact that this is still a solution. Okay? So this is one example of variable symmetry. So another model for the n queens problem is to choose one queen per column and the value represent the row. Okay? And so in that case, you still have a symmetry problem because you can flip like this vertically. You can flip vertically the solution, okay, like it's a mirroring, vertical mirror here that you have, and you still have a solution, okay? So if you decide to split it and Q1 becomes Q8, Q2 becomes Q7, Q3, Q6, Q4 becomes Q5, okay? You've got a bijection and you still have a symmetry. So this is still a variable symmetry, okay? And it's not so easy to avoid that symmetry for the n queens problem, okay? The value symmetry is also defined using a bijection, but the bijection that you have is defined on the values. So if this is your solution, you apply the bijection on the value here, and you keep the variables the same, orders. If it's still a solution or non-solution mapping, then you have a value symmetry. Let's look at one example. This example is the graph coloring problem. So the graph coloring problem, you are given a graph and you want to find a color for each of the nodes such that two adjacent nodes take different colors. Okay? So my variable is for each node, I've got one variable and the value will represent the color. If I decide to flip the color, to do a bijection between the colors, then I still have a solution. Okay? For instance, you could take the modular number of each colors, and so you found a bijection that works, that will preserve the solution and non-solutions. This is a value symmetry. This is not a variable symmetry, but this is a value symmetry. We want to break the symmetries because by breaking the symmetries, hopefully we will explore a smaller search space. There are two different strategies to avoid the symmetries. One is called the static symmetry technique and the other one is called the dynamic symmetry breaking technique. The static symmetry breaking technique just add new constraints to the model or try different variables. Okay, so this is just a modeling trick. This is at the level of the model. Okay, that you can act on the breaking of the symmetries using static techniques is at the modeling level. The dynamic symmetry breaking is during the search. Okay, so it's a different technique, but you will enforce the breaking of the symmetry during the search. And usually it requires you to implement a custom search to break the symmetry. Usually this technique is a little bit better. Okay, if you can use this technique, but it's not always possible to use it, you can use that one. But this one is easier, so it's also interesting to understand it. Let's review the breaking of the symmetry techniques on the bin packing problem. So the bin packing problem is pretty similar to the Stillman-Slab problem, but it's easier. You are given n objects, you are given the size of each of the objects, you are given n bins, and you have a fixed capacity for the bins, which is the same for all the bins. And what you want to do is to find a bin for each object such that the capacity of the bin is respected. Okay, so this is one example. You see here, the capacity is fixed there, and you want to assign all the objects to different bins such that respects the capacity of the bin. This bin packing problem is NP complete, so it's a difficult problem, and it contains many symmetries. I guess you can realize that I have already a value symmetry here because I can swap the values of decided for these orders and these orders, and I will still have a solution. So swapping the content of the bins, which is a value symmetry, because you change the values of some of the variables, will lead to symmetrical solutions. Okay? So that's one symmetry that we want to avoid. Two different approaches, as I said. There is a static one that consists at adding constraints to the model, and there is a dynamic symmetry breaking technique that will add constraints during the search and do specific action during the depth first search exploration. But both techniques aim at the same goal, which is reducing the search space exploration. So we want to avoid the swap between two different bins. One possibility is to impose an arbitrary order on the bins. For instance, we could count the number of items placed in each of the bins. For instance, I introduce a new variable to represent that. Or I could also decide to capture the load of the bins, and I will just impose that the load is decreasing or that the number of items placed is decreasing. If I impose such a constraint, I will avoid value symmetries a lot. Okay? So for instance, here you see that I have 3 items, 2, 2, 3, 3, 3. This violates my decreasing number of items placed in the bin, so I want to have them in that order, which is not the case. Okay, if I would have imposed a specific order, maybe I would have avoided some symmetries. That's for the static symmetry breaking constraint. Okay, so if I want to enforce this, assuming that the load variable is represented by L, so I could say Lj is larger than Lj plus 1, and so the load should be decreasing. Okay, I can impose a constraint like that, and I do that for every j. There is one drawback with static breaking of the symmetries with constraints. The problem is that maybe you were solving an optimization problem, and the first solution that heuristic was able to find is this one. Then you realize that there were symmetries in your model, and you had added new constraints. The problem is that this previous solution that you were able to discover, because of the new addition of the constraints, now has disappeared. Okay? And the next one that you will discover is much more far in the search tree. And so there is a kind of bad interaction sometimes between the new constraints that you have added and the objective function and the solution that you were able to discover pretty quickly in the search tree. Sometimes the problem is that you suppress solutions And these solutions that you have suppressed, they were the ones that were discovered quite early by the search tree, and they might not exist anymore. So there is sometimes a bad interaction with the heuristic. Be careful with static symmetry constraints. Sometimes it helps, sometimes it doesn't help. This is why, if you can, you should maybe consider this dynamic symmetry breaking technique that does not suffer from the bad interaction with the heuristic. The idea is the following. Let's come back to the Stillman slab problem. I have a new order that I decide to place, okay, and these are all the possible slabs that remain. And I want to explore an NRE search tree. So I will explore a search tree in which I will try one branch under the search node for every possible values in the domains. So clearly this order cannot be placed anymore into this slab because it's already filled, right? It's completely full. But I still have slab number 4, 5, 6, 7, 8, and 9. And as you can see, at this specific stage in the search tree, the slabs are completely empty. 4, 5, 6, 7, 8, and 9 didn't receive any order yet. Do you think that it's worth considering all of them and creates 1, 2, 3, 4, 5, 6 different branches under this node? Probably not. It's not worth to explore all of them because they will lead to symmetrical search spaces. Instead, we can realize that we could arbitrarily decide to put that order into the bin number 4, into the slab number 4, and not consider 5, 6, 7, and 8 alternatives because they are completely equivalent. Okay? And so what I will do for the bin packing problems like these ones is that I will consider, instead of considering 4 different placements that are completely equivalent, I will consider only one of them. For instance, that one. Okay? And this is what we call dynamic symmetry breaking during search. Okay? So instead of doing this, instead of trying them all, I will try only the 3 first ones. Okay? The one that are already occupied plus one empty one, but at most one that is empty. During the practical session, you will implement the OR constraint using the watch literals. You will implement the is-OR constraint, and you have also some to-do in the Stillman slab model. First, you need to model the objective. You need to model the color constraints using the is-OR constraint that you just implemented before. And you will add new redundant constraint for the bin packing problem. And finally, you will break the symmetries using a static technique and using a dynamic technique during the search.